The James Webb Telescope has discovered a black hole 70 million light-years distant, shocking astronomers and actually upending our preconceived notions about the energy sources of active galactic nuclei with its shockwaves of gas and dust. However, what are a few of the most striking events that have occurred in the cosmos depths? Why do they defy our existing models, and why might the mass monster still be able to assist us unravel one of the biggest riddles in contemporary space exploration? They are regarded as cosmic omnivores, massive devastation machines that obliterate everything in their path. However, this is only part of the reality of black holes. However, it is undeniable that because of their great compactness, these gravity monsters have the destructive ability to irretrievably gobble up anything that gets in their way. It is necessary to examine the following example in order to comprehend the meaning behind this frequently mentioned compactness. A hypothetical black hole with the mass of the Sun would have a diameter of 2.9 km, while one with the mass of the Earth would not even come close to reaching the 1 km threshold. Nothing that has passed a black hole's event horizon can return from the interior to the outside, because to the unmatched gravity that arises from this, no matter, no radiation, and no information, to be exact. The strange objects behave like any other typical large body outside of the cosmic death zone, and this is the deciding element. Other celestial bodies can readily orbit them in unstable orbits. Even though they still have a lot of unanswered questions, supermassive black holes, which can be millions or even billions of times as large as the Sun, are thought to be essential to the development of galaxies. Not only that, but astronomers now believe that the Milky Way is not an exception to the rule that nearly every galactic center is ornamented with a supermassive representative of these cosmic monsters. Sagittarius A is the name of our primary black hole, which is around 4 million solar masses in size. The galaxy with the rather cumbersome label ESO-IOA is home to the spectacular black hole that is now making news in astronomy for its unexpected shows. One participant of the Galactic Activity Torus and Outflow Survey, or GATOS project for short, is a lecturer at Newcastle University. This research partnership just made a groundbreaking finding while studying the nuclei of neighboring galaxies with the James Webb Telescope. According to the introduction, the galaxy in question is around 70 million light-years from Earth and is home to an active supermassive black hole at its core, which eats up the surrounding matter in a voracious manner and emits bright light that spans the electromagnetic spectrum. A bountiful cosmic feast that other black holes could only imagine is available to the behemoth in this context. Let's examine Sagittarius once again. The amount of matter surrounding our black hole is actually so small that it is comparable to a human consuming a grain of rice every few million years. Despite having several noisy neighbors, Sagittarius A is regarded as a calm black hole because of its cosmic force diet. These include, for instance, the supermassive black hole M87, which is located approximately 55 million light-years away and is enthroned in the core of the gigantic galaxy Messier 87. With 6.5 billion solar masses, it is not only much larger than Sagittarius AA, but it is also encircled by an enormous amount of gas and dust, which continuously adds new material to the structure. However, the matter's angular momentum prevents it from falling straight onto M87. Instead, it creates an accretion disk, a swirling, flattened cloud of gas and dust that progressively feeds the black hole inside. Supermassive black holes like M87 do not, however, have the ability to passively await feeding. On the contrary, the accretion disk heats up to 10 million degrees Celsius, as a result of the massive tidal forces created by the Colossus's intense gravitational pull. The accretion disk then shines brightly due to the tremendous heat, adding to the luminous display of the active galactic nucleus. How a shock causes astronomers to reevaluate their method. The surrounding food does not entirely wind up in the maw of a black hole, regardless of how ravenous it is. Some of the stuff in the accretion disk is directed towards the black hole's poles by the high magnetic fields, which accelerates the charged particles to nearly the speed of light. In turn, this matter is flung outward in parallel jets from the mass monster's two poles. These jets are accompanied by emissions over the electromagnetic spectrum, particularly radio waves. These forces combine to make active galactic nuclei so luminous that they can outshine all the stars in their parent galaxy. In the past, telescopes were frequently unable to see the throbbing hearts of galaxies despite their immense luminous power. This is because visible light and other electromagnetic radiation wavelengths are absorbed by the dust that surrounds the active galactic nuclei, obstructing our terrestrial vision. Fortunately, the James Webb Telescope was built especially for infrared astronomy, because infrared light can penetrate the veil of dust. In light of this, the most potent space telescope ever created is the ideal means of gaining access to the secret locations of active galactic nuclei. Upon turning that key in the galaxy ESO, the GAATOS team found that, contrary to what was previously believed, collisions with gas jets may be the source of the energy heating up this whirling cloud of gas and dust. To put it mildly, the scientists were surprised to discover such a shock structure, but it demonstrates the massive impact that black hole radiojets may have on their surroundings. In summary, the dusty shock might also have a lot more knowledge-gathering potential. Experts could learn more about how galaxies recycle their material and the precise ways in which the gravity monsters affect galaxies in general by examining the dust surrounding supermassive black holes. Seldom does a central black hole occur by itself. Astronomers Bruce Balick and Robert Hanbury Brown detected an unknown radio source in the constellation of Sagittarius from ESO 428-434. However, they were unsure of what they had truly located in the far reaches of space. This radio source's identity as a black hole was only discovered through a series of observations made over a number of years, starting in the 1990s. However, recent data really indicates that Sagittarius A is not alone but is joined by an incredibly uncommon representative, a so-called intermediate black hole. This suggests that the next cosmic revelation may be on the horizon. However, we must first keep in mind that a black hole can only be found by the gases that circle its event horizon and the impact it has on neighboring stars. This will help us to comprehend how such a behemoth might be found. The blazingly bright celestial bodies are accelerated to record speeds, and their light is distorted by the black hole's immense gravity. As the gas clouds needed for this would be ripped apart in a moment, one would expect that new stars shouldn't even form in such severe areas. In actuality, however, scientists discovered many protostars that lie dormant in the near region of Sagittarius AA, along with their dust cocoons. In summary, these star newborns are located just 0.1 to 0.3 light-years from the black hole. However, how did they overcome the harsh circumstances in their home? In fact, the group headed by Florian Paikir from the University of Cologne likewise tackled this very subject. The impossible protostars are found in the star cluster IRS-13, whose motion data the researchers examined. As the largest and densest coherent structure in the near region of Sagittarius AE, IRS-13 was ultimately going to stun the specialists. After examining over 50 star orbits, the researchers discovered a novel structure that initially perplexed them. The stars in the deeply embedded cluster follow ordered orbits that cannot be explained by the effect of Sagittarius A alone, the scientists discovered when they spotted a disk-like system in the cluster. In addition, IRS-13 proved to be significantly bigger than initially believed. However, what precisely keeps the cluster together and affects the star's orbits? The astronomers also used information from NASA's Chandra X-ray Telescope and the ALMA Observatory to get the answer. And sure enough, the dataset revealed that IRS-13 had a zone where ionized gases rapidly orbit around an invisible center. This implies that the impacted star cluster has an intermediate black hole of 30,000 solar masses, Paikir said. Almost no research has been done on this kind of black holes, which is thought to be a potential forerunner of supermassive black holes. According to current theory, IRS-13's star association is held together by the gravitational pull of the intermediate black hole, which also serves as a stabilizing antipole to the gravitational pull of the far more massive black hole Sagittarius A. Space science would benefit greatly from an absolute sensation if the existence of Sagittarius AA's star sister is verified for two reasons. On the one hand, there are very few intermediate black holes. On the other hand, there are only a few recognized possibilities. However, They are thought to be a potential transitional form between the supermassive forms in galactic cores and stellar black holes from supernovae. The collisions of these intermediate forms may lead to supermassive black holes. The specialists are now preparing to verify their intriguing theory in upcoming observations, which suggests that IRS-13 may include a crucial component for the development of Sagittarius A. Please feel free to test your subscription status immediately. If you haven't already, please click subscribe so that you don't miss another thrilling video from us.